With the duration measure, we assume that there is a linear relationship between the change in YTM and the change in bond price. And just to illustrate that point, let's look at this picture. Here we have the actual bond price at different YTMs. Let us say that at a given point in time, the YTM is 10% and the bond is priced at par, which is 100. If interest rates go up from 10% to 11%, then according to the duration measure, the price of the bond will come down in a linear fashion to this number. And if interest rates go from 10, let's say, to 9%, then according to the duration measure, the price of the bond will rise to this point. Essentially, this tangent tells us about the impact on the bond price of a change in YTM, and you can see that this is a linear relationship. But the actual price yield relationship is not linear, it is convex. When you look at the graph or the curve from the origin, it makes a convex shape, and the degree of this curvature is called convexity. So in this section, we are going to talk about bond convexity. Clearly, when we want to estimate the change in bond price to a change in YTM, there is a component related to duration, and then there is also a component related to convexity. And if we think about it, let's go from 10% to 9%. This distance from here to here is the estimated change due to duration, and this distance from here to here is the estimated change due to convexity. And this distance is called the convexity adjustment. It is a number that we add on to the answer that we will get using duration. What if interest rates go up to 11%? Then according to the duration measure, the bond price will be here, but then we add this amount, which is the convexity adjustment, to get closer to the actual bond price. Let us look at the formula now for convexity. The approximate convexity is given by this formula, which you need to learn. All the symbols should be familiar. PV minus is the value of the bond when the interest rate goes down. So if the interest rate goes down from 10% to 9%, then PV minus is this value, plus PV plus, that is the value of the bond if interest rates go up, minus 2 times PV naught, that is the original bond price, yield squared. In this example, the yield is 1%, but I hope you remember that in all our duration and convexity formulas, we plug in the yield as a decimal. 1% becomes 0.01 squared, and then PV naught, which would be 100 again. I can't give you an intuition for this formula, but you do need to memorize this formula. So what is the change in the value or the full price of the bond? It is given by duration plus the convexity adjustment. The duration part you have studied before. This is simply the annual modified duration times the change in yield, plus half into the convexity adjustment that we calculate here, times the change in yield squared. Let us practice this concept using example 13. And I want you to read this and try doing it on your own first. Here is what you need to do. First part is calculate the full price, and we've done this several times, but I will do it again for you. We plug in N is 15 into the calculator, interest rate is 7.44. Note that this is an annual coupon bond. The payment is equal to 7.25 because that's the coupon rate. Future value is 100. You compute the PV. This PV would be at the start of the period, but we are told that settlement happens 83 days into a 360-day year. So the full price on settlement date would be this number, 98.31658, multiplied by 1.0744 raised to the power of 83 over 360. So the full price on settlement date is this number. This is also PV not in our formulas. Then we compute PV plus using the same procedure, but PV plus is the interest rate assuming a 1 basis point increase in interest rates. We will use then an interest rate of 7.45, and using the same procedure we will get PV plus equals 99.869964. PV minus would require using an interest rate of 7.43, and here is the full price. The change in yield is 1 basis point, which corresponds to this number in decimal. With these four variables, you can plug into the duration formula, which is PV minus PV plus divided by 2 into yield into PV naught, and you should get a duration number of 8.6907. For convexity, you take these numbers and plug into this formula. And when you do that, the answer that you should get for approximate convexity is 107.046. Then part 3 asks us to calculate the estimated convexity adjusted percentage price change resulting from a 100 basis point increase in the yield to maturity. Now we need to use this formula. So the percentage price change is given by the duration component and then the convexity adjustment. We have calculated the modified duration. The change in yield is going to be 1%, which means that we'll use a number of 0.01 and then half into the convexity number, which we just calculated, and then yield here would be 0.01, but note that we use a square. So plug in the numbers into this formula, and what you should get for the percentage change in price is equal to the percentage change in value of the bond then is minus 0.08155. That's expressed as a decimal. Expressed as a percentage, the answer would be minus 8.155%. And finally, compare the estimated percentage price change with the actual change, assuming the yield to maturity jumps to 8.44%. What we are saying in part 4 is that we want to compare this number, which we have calculated using the formula shown over here, with the actual change in price. For the actual change in price, we use this model, but instead of plugging in an interest rate of 7.44, we plug in an interest rate of 8.44. If we plug in 8.44 and then use the same procedure, what we will get is 91.780921. And if we look at the percentage change from here to here, that answer is 8.179%. And notice that these two numbers are quite similar. So once we take duration and convexity adjustment into account, then the change that we calculate using this formula is quite close to the actual change, and that is the point which is illustrated over here. Let us now consider the impact of convexity on a bond investor. Say we have two bonds, bond B and bond C. As you can note over here, bond C is more convex or more curved relative to bond B. Say that at a given point in time, both bonds have the same YTM of 10% and the same price, which is 100. What will happen if the yield to maturity goes from 10% to 9%? Note that the appreciation of bond C is more than the price appreciation of bond B, and that is because bond C is more convex. Now what happens if the yield to maturity goes to 11%? Here, if you look at bond C, the depreciation is this much, whereas for bond B, the depreciation is greater. And this illustrates the fact that convexity is good for a bond investor, because when rates go down, the bond which is more convex appreciates more, and when rates go up, the bond which is more convex depreciates less. Next, we need to understand the factors which impact convexity, and this is easy to remember because most of the factors operate in the same way that they did with duration. So if you have bonds with higher time to maturity, if you recall, higher time to maturity generally led to greater duration, and similarly bonds with higher time to maturity have higher convexity. With coupon rate, bonds with lower coupon rates, and if we take the extreme example of a zero coupon bond, lower coupon rates meant higher duration, and lower coupon rates also result in higher convexity. Yield to maturity, we have greater duration if YTM is small, and we also have greater convexity if YTM is low. The final point is dispersion of cash flows, and this is different from duration in the sense that if you have two bonds A and B with the same duration, but bond B has a greater dispersion of cash flows, which means that cash flows are more spread out, then the convexity is higher. So the greater the dispersion of cash flows, all else equal, the convexity will be greater. Example 14 illustrates these points. It is fairly tedious, but everything that you see here is just a plug and play into the various formulas that we have discussed. We are given the basic information, and then we are asked to calculate approximate modified duration and approximate convexity for each bond. The two bonds here, one is a 30-year bond and the other is a 100-year bond. Even without doing the calculation, I hope you have now an intuition for the fact that the duration is going to be higher for the 100-year bond and the convexity is also going to be higher. When you do the calculations, what you should get is the following. For the 30-year bond, the approximate modified duration is 17.38 and the convexity is equal to 420.80. For the 100-year bond, what you should get is a duration of 24.5 and a convexity of 1132.88. So notice that with the 100-year bond, the duration is higher as we expected, but the convexity is much higher than the convexity of the 30-year bond. You can do the calculations and also check the calculation in the curriculum. As always, I want you to use the calculator to come up with bond prices. Effective convexity. Hopefully this term effective rings a bell. We talked about effective duration before, and if you remember, with effective duration we were dealing with bonds with embedded options as well as mortgage-backed securities. So if you have a bond where the cash flow is not deterministic, in other words, the timing and amount of cash flow is not known for sure, then it is inappropriate to use Macaulay duration or modified duration. Then we use effective duration. And with effective duration, we take changes in the benchmark rates or changes in the benchmark curve. The same applies to effective convexity. The effective convexity of a bond is a curve convexity statistic that measures the secondary effect of a change in a benchmark yield curve. It is used for bonds with embedded options. And to this we can add mortgage-backed securities. In fact, this is essentially bonds where the cash flows are not known for sure. This is the formula. It is almost exactly the same as what we've seen before, but instead of using the change in yield, we use the change in the benchmark yield curve, which is given by this expression. I also want to point out that callable bonds have negative convexity. If this is your regular straight bond, it is convex. Here we have price on the y-axis and yield to maturity on the x-axis, or you can just generally refer to this as interest rates. What happens for a callable bond? We've seen this before, and I will draw a callable bond in a different color. At high interest rates, the price of a callable bond will be fairly similar to the price of a non-callable bond. But as interest rates decrease, the value of the callable bond will digress from the value of a straight bond because the bond is likely to be called at low interest rates. Notice that over here, the shape is not convex. This is concave, but generally this is referred to as negative convexity. Negative convexity also implies that over here the interest rate sensitivity is much lower than the interest rate sensitivity of a straight bond.